We start this unit on matrices, talking about just basic operations, adding, subtracting, multiplying by what we call a scalar. Here in this first paragraph, we have a matrix is an organized rectangular array of numbers, and a determinant is the value associated with a square matrix. Determinants we talk about in another lesson. The earliest known example of numbers being placed in an array in order to aid analysis is clay tablets from Babylon in the 4th century BC. Matrices are tools for organizing and storing information. Management of information such as cost of materials, time to produce each item, available inventory by month, needed inventory, and so forth provide material to create a variety of matrices, develop definitions, and basic matrix operations. Dimensions and dimension labels are used to provide rationale for addition and multiplication procedures. Emphasis is placed on interpreting entrants as matrices are written, added, multiplied by, again, what we call scalar and regular multiplication, and transposed. Properties of real numbers are examined to determine which properties are true in matrix operations. Determinants are used to find area of triangles and test for collinear points. Systems of equations are written as matrix equations, and inverses of coefficient matrices are used to solve the systems. So we're not going to really do too much with matrices. We're just going to do the basics. There's a whole course in college called linear algebra, which deals with solely matrices. So here we're just going to kind of get a little taste of matrix operations, and then we're going to also use it to help us solve systems of equations. So what we've done back in the beginning of the course. So to get us started here, we're just going to kind of set you off with, here we have what we call a matrix. We have what we call the vertical column, or the vertical parts are your columns, like the columns of the Colosseum or something are vertical. And then you have what we call rows. So the way that we write the dimensions are your rows by the columns. So how many rows we have is the first number, and columns is the second one. So in this first example, over here on the left, there are 3 rows in this matrix and 3 columns, 3 vertical. So this would be what we call a 3 by 3 matrix. In this next one, there happen to be 3 rows and 2 columns. So the dimensions of this would be 3 by 2. And in this last one, although there are only one number each, there are 4 columns in this matrix and only 1 row. So this would be 1 by 4, rows by columns. 2 matrices are equal if and only if all corresponding entries are equal, which we'll talk about a little bit down the page a little bit. Just a few things as we go over this. Entries, oops, I forgot that word. All corresponding entries are equal. Entries happen to be the numbers that are actually in there. So the entries in this left one would be 1 would be an entry, -2 is an entry, 5. So that's just what those entries represent. Special kind of matrices. So you have a row matrix. A row matrix is a matrix with only 1 row. And you can do any example you really like. They don't have to be the exact numbers of mine. So here I have 8, -1, and 5. That represents the row matrix. A column matrix is a matrix with only 1 column. And then the row matrix, or the column matrix, would be, again, it doesn't matter the numbers, the entry numbers. So 6, 5, and -2. A square matrix is a matrix with the same number of rows as columns. So when we talk about what that looks like, there's a couple different, you can have a 3 by 3, a 2 by 2, a 1 by 1. So here I'm going to make a 2 by 2, 2 rows and 2 columns. And then I'm just going to do a 1 by 1, which is just one number. A few things of note: when we read matrices, we always go across the rows first. So I would read this one as 5, -2, 8, 1. So across the rows and then down. And then a zero matrix is a matrix with only zeros as entries. And it doesn't matter which size the dimensions are. It could be something that is a 1 by 3, or a 1 by 1, or a 2 by 2, or a 2 by 3. It doesn't really matter, as long as all the entries are zeros. In this first example, it says find the value of each variable. So what I'm going to do is I'm going to highlight, here I have a 2 by 2 on the left. This matrix is 2 by 2, and this matrix is a 2 by 2, so they are in fact equal only if their corresponding entries are equal. So for example, I have an x plus 5, that has to equal 2. So that's how we're going to go ahead and find out what x equals. I'm going to say x plus 5 equals 2. And then I'll subtract 5, so we get x equals -3. So that would be the answer for x. Now again, some of the other ones that you'll notice, -1 corresponds to -1, they equal one another, and 4 corresponds to the 4. So then that only leaves us to take 6, has to equal 3y. So that equation would be 6 equals 3y, or a y value of 2. For part B, although it looks a little bit more complex, it's not so bad. I'm going to go ahead and start by highlighting my x value. So here, my x is right here, and that would correspond to the -1. So x equals -1. And then finding my y is along the top row in the 4th column. So that has to equal 6, which is in the top row, 4th column. So y would equal 6. And the last one there, we have to find our z. Z is right there in the second matrix on the right side, and that will correspond to 4. So x would equal 4. For number 2, it says to simplify, and for here we're going to be adding our matrices together. So the first thing we want to always do is measure our matrices, because they can only be added or subtracted if they have the same dimensions. So we have to make sure that they are the same dimensions. Now, part A, they look pretty obvious. So again, we're just going to practice labeling. There are 3 rows, again, 1, 2, 3, and 2 columns. So this would be a 3 by 2 matrix. And the second one is also a 3 by 2 matrix. So since they are the same dimensions, we can we can add them together. When we add them together, we are also going to have a 3 by 2 matrix. So I'm going to take this 4 and add it to the corresponding entry of 2. So 4 plus 2 is 6, and 7 plus -5 corresponds to that. So when I add 7 and -5, I get 2. 0 plus -3, -2 plus 2, 1 plus 0, and -4 plus, or -6 plus -4, and that would be the answer to part A. Part B, maybe you can see it right away, but this is what we call a 2 by 2 matrix, and this is 1 by 2, so this is 2 by 2, and this is 1 by 2, and they are not the same dimensions, so this one is not possible. So, not possible. And usually we ask you to write why it's not possible, and you can say dimensions are not equal. for part C, just be careful, we are subtracting, so you're going to subtract all your corresponding entries. So again, this is a 3 by 3 matrix, and also the second one's a 3 by 3. So our final answer will also be a 3 by 3 matrix. And again, we're going to subtract, so I'm going to just start the first couple. So 1 minus 2, and negative 7 minus negative 2. Now be careful, negative 7 minus negative 2 is the same as negative 7 plus 2. And then in the 3 minus 0. Now at this point I'm going to go ahead and fill in the rest of the matrix just by subtracting. So 2 minus 5, 0 minus negative 6, negative 1 minus 8, 4 minus 10, negative 6 minus 2, or negative 4 minus 2, and 2 minus 12. So we end up with a 3 by 3 matrix, as you see there. Now for part D, this is what we call a scalar. It's a number that's outside. It kind of looks like a coefficient, and it's identical to what you think it would happen. This negative 3 means that you're going to multiply this entire matrix by negative 3, every entry. So it'll still stay a 3 by 3 matrix. It doesn't change the dimensions, it just makes everything multiplied by negative 3. So the top row there would be negative 3, negative 6, and negative 9, negative 27, 6, negative 18 in the second row, and then in the third row, negative 30, negative 12, and 15. In problem number 3, it tells us that it gives us two matrices. It gives us a 2 by 3 and a 2 by 3, A and B. Matrices, just a side note, matrices are represented by capital letters, so we'll never use a little a to represent a matrix. So here we have, it tells us to take matrix A and multiply it by negative 2, and then add matrix B to it. So the first thing I'm going to do, and maybe I'm going to take negative 2 times A, and I'm just going to do that without writing it down. So again, multiplying everything in this matrix by 2, well, negative 2. And that gives me negative 2, negative 6, and 4 in the first row, and then negative 8, 0, and 10 in the second row. And then matrix B doesn't have a scalar that it's being multiplied to. I'm just copying that down. And the last step is just to add your corresponding entries. So it'll stay a 2 by 3. So when I add negative 2 plus 3, negative 6 plus 1, and 4 plus negative 5 for the first row, and then negative 8, and 0 plus negative 7, and 10 plus 2 for my second row. For number 4, this is a matrix equation, so our answer is actually going to be a matrix, and the matrix is going to be x equals in the end. So the first thing I'm going to do is make everything in this right-hand side multiplied by 2. So I'm going to go ahead and do that. Again, remember capital letters for matrices. So the first thing I'm going to do is just keep the left side of this equation the same. But on the right side, I'm going to multiply everything by 2. So I'm doubling all the numbers inside there. And then again, just like any other equation, I want to get x by itself. So I want to subtract this matrix to the other side of the equation. So the matrix on the right will stay negative 2, negative 8, 0, and 12. But I'm going to subtract the matrix that I just talked about on the left. When you subtract them, you get 0, negative 9, negative 3, and 12. Now the last step, just be a little cautious, and it's something that you're not sure, that not typically you would divide by 3 at this point. Now in matrices, we don't really divide by a number. You want to take this entire matrix and put a division sign underneath of it and put a 3 under there. What we're going to do instead, which we've done before in the past, instead of dividing by 3, I'm going to multiply that matrix by a scalar of 1/3. So again, instead of putting the division sign, just it's the same reason as why we don't put like y times 3. We write 3y. So in math, we just don't do it. So multiplying by that scalar, you get x equals 0, -3, -1, and 4. So all I did was multiply each of the numbers inside of this matrix by 1/3, and that gave me 0, -3, -1, and 4. So that would be the answer to that matrix equation. I'm going to go ahead and let you try that last one, part B. To get you started here, the first thing you're going to want to do is you're going to want to add the 2 matrices on the inside, and then you multiply by 2, and then the left has to equal the right. So I'm going to go ahead and do that as well. So if you want to just pause the video where you are, complete the problem, and then come back to see if you have the right answer. And for this problem, part B, I ended up with an x value of 3 and a y value of 9. Now remember, once I multiply everything in this matrix by 2, I end up with this 2 by 2 matrix you see here. And then you have 2 matrices that are equal to each other if and only if their entries that correspond are equal. So I highlighted my corresponding entries, set them equal to each other down here below. In the next 2 examples, we're going to organize the information about, in the first one, healthcare plans. In the second one, it's talking about healthcare plans, but we're going to actually figure out just a small little problem about it. So here we have 2 different things. We have on the top, we're talking about healthcare plans for this year and next year. And we have an individual plan, we have a comprehensive plan, HMO standard, and HMO plus. So we have the 3 different costs for each of them. So you have an individual type, and there's 3 different types of that, and again the cost for that. And for families, you have comprehensive, HMO standard, HMO plus, so that you have the same 3 types, but of course, because you're dealing with families, more people mean higher the cost. So that's for this year. And then we have for next year as well, the same thing, and you see here the costs are different for each of them. So we're just going to organize this in a matrix. So I'm going to do 2 matrices. I'm going to do for this year, and then we'll have one for next year. And we're going to we have individual, and we have family. And we have 3 different types for each of them. So you have comprehensive, which I'm just going to abbreviate COMP. We have HMO standard and HMO plus. And then I'm just going to go ahead and put all the values into this matrix that we see above. So I'm going to go ahead and pause it and write them in. You can as well. So here's what this matrix would look like once I filled in all the numbers. So I just took all the information that was in this first paragraph and put it here in a matrix to organize it. And I'm going to do the same thing, and I'm going to use the same labels for next year. I'm just going to use a different color. So we're going to still have individual and family. We're still going to have comprehensive, HMO standard, and HMO plus. So they're the different types of health care plans you have. So go ahead and pause, write all the numbers that we have in there, and I'm going to pause and do it as well. And here's how the second one looks here on the right, with all the numbers again, from the second paragraph that says next year, that's what all these numbers came from. And the last problem here, number 6, a company offers the healthcare plans in the previous problem to its employees. The employees receive a monthly paycheck from which the healthcare payments are deducted. So that's kind of important. It's monthly. So there are 12 paychecks that they're going to spread this out amongst. Use the matrices in the previous problem to write a matrix that shows the monthly cost in healthcare plan from this year to next. So the first thing that we want to do is we know it's going to be 1/12 because it's one, every 12 or every month they're going to get deducted money over the course. So up here in the previous problem, this is for the entire year. We only want for 1 month. And then we're going to subtract B minus A. So we're going to take the cost, I guess maybe I should label it. We have, this is my A, this is my B, or this is my A, this is my B. So I'm going to subtract next year and this year. So when I do that, meaning I'm just going to take, for example, 683.91, and I'm going to subtract 694.32. So here, if you try to read this for individual comprehensive plan this year, it's actually higher than next year. So it's going to go down next year for an individual in the comprehensive plan. So when we go ahead and subtract them in this one, the very first entry would be negative because it's actually decreasing. And then I'm going to go ahead and subtract 1699.48 minus 1725.36, and that gives you negative 25.88. Continuing to do that, you have 1130 as a difference in the HMO standard for the individual, 29.69 for the HMO standard for the family plan. 9.79 is the difference in the HMO plus for the individual, and 24.96 for the family and HMO plus. And now we're just going to simply multiply all of those numbers by 1/12. In your calculator, you can go ahead and just take negative 1041 divided by 12. It's just in notation that we don't divide by on paper. So in your calculator, you're just going to do the division. So there's a difference in a paycheck. You actually get less money taken out next year for the comprehensive plan. However, for the HMO standard and the HMO plus, that will actually increase by 94 cents for an individual and $2.47 for a family. And for the HMO plus, it'll increase by 82 cents, how much they're taking out in your paycheck, and $2.08 for the family.